Okay, so we got this thing, some sort of tube with a handle attached to it, attached to the wall. Um, at the point that we're worried about, it's got a circular cross section with a like I said, it's a tube, so it's got a 50 millimeter outside radius, 40 millimeter inside radius, and then there's a force applied to the handle there, uh, 60 kilonewtons. The offsets in the y direction and the offset in the x direction are both 300 millimeters from the point of interest. So essentially, if we want to do this, the easiest way to go about that is to figure out an equivalent force couple system at where that where that section's taken, that will have the same effect as the six kilonewton force. So essentially, if we want to do so, we can just kind of do it piecemeal. So we know it'll be a 6 kilonewton force, obviously downwards, but if we took this force here and moved it over here, then we could do that by also applying a 6 kilonewtons times 300 millimeter moment that is about the y-axis. So yeah, that's right here. So 6 kilonewtons times 300 millimeters. So that'll be a 1.8 kilonewton meter moment, and that'll be a torque moment once we get to the point of interest. So that's moving that one there. If we want to take that force couple system and then shift it over to the point we're looking at, then we just need to have force downward and the moment about the y-axis that we already calculated, and we're also going to need a moment about the x-axis. So the moment about the x-axis would be, again, 6 kilonewtons times 300 millimeters, 1.8 kilonewton meters, because the distances were the same, so the moments end up being the same. That having been said, we are interested in this spot right here, so the spot at A. So that point A is located on the neutral axis for bending about the x-axis. So as a result, this moment here doesn't come into play. That one, at that point at least. If we picked a different point, obviously it'd be causing stresses. But at that point, it's on the neutral axis for bending about that axis, so it doesn't come into effect. The stresses that do cause it are the torsional load, caused by the bending moment about the y-axis, and the shear load. So the shear load is going to cause transverse shear. The torsional load is going to cause torsional shear. And that's about it. So there's no axial load. The bending moment about the x-axis doesn't cause any stress there. So that is it. So just looking at kind of an so here's the cross section that we're looking at here. We've got a little cube there at the corner that we're at the point that we're examining. So directionality is important. So the shear is basically going to be pushing downwards on this face. So it's going to cause some sort of shear forces that are oriented. So they're going to be oriented to some degree kind of slantwise over here, but at the point we're looking at, they're going to be pointed straight down. So they're going to be a force that's pushing downwards on the positive y face of this little cube. The torsional load, however, so I'll just kind of go back up here. So the torsional load is caused by the rotation about, come on, the rotation about the y-axis. So basically we're pushing it down and kind of causing this thing to want to rotate. So when we get to here, it's going to be basically causing shear forces that act counterclockwise as we move about that cross section. So when we get to A here, because of A's location, those are going to be acting upwards. So as a result, the shear stresses caused by the direct shear and the shear stresses caused by the torsion, they cancel out somewhat. So when we add, basically when we add those together, one of them will be negative, and we need to account for that. So let's go ahead and calculate what those are. So first off, we're going to need to know our J value. So if we want to figure out what the torsional stress is, so again, J is for a tube-like structure is going to be pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. So pi over 2 times 50 millimeters to the fourth minus 40 millimeters to the fourth. That gives us 5.8 times 10 to the 6 millimeters to the fourth. So we can use that to figure out what our torque is. What our stress due to the torque is. So we know that the torque about the y-axis is 1.8 kilonewton meters. The C point, so the point that we're looking at, that's just on the outside of the skin here, so that'll be at the 50 millimeter mark. And then J is obviously what we just calculated, so 1.8 kilonewton meters times 1,000 millimeters per meter, so we can cancel those out, times the 50 millimeters divided by 5.8 times 10 to the 6 millimeters to the fourth. Then, this millimeter and this millimeter cancel out 2 of those millimeters, leaving us with kilonewtons per millimeter squared, which ended up being a small number when we convert it to newtons per millimeter squared, and so multiply by 1,000, and that gives us megapascals. We get 15.5 megapascals. So again, that is on our little cube here, that's going to be pushing up because it's acting in a counterclockwise fashion. Our transverse is just based upon VQ over IT. So the shear term, the shear load term, is 6 kilonewtons. Our I is, well, it's just half of J, or if you want to calculate it directly, it's pi over 4 times the radius to the fourth minus the outer radius to the fourth minus the inner radius to the fourth. So 2.9 times 10 to the 6 millimeters to the fourth. Our Q calculation, so that's going to be based upon like the Q for the entire section, the entire circle, minus the air in the tube. So basically, we just did, and then Q obviously is just the AY bar. So again, neutral axis we know is at the center, obviously. The Y bar for a circular section is at 4r over 3 pi from there. So kind of right about there-ish, I guess. Our area for a half circle is pi r squared over 2. So our Q, found by multiplying those two things together, we can factor out the pi over 2 and the 4 over 3 pi, put those in front, and then cancel out the pi's, not the 3, I meant to can't. I love how when I hit undo, OneNote doesn't remember what order I placed things in. So cancel out the pi's. So this term here ends up being 4 over 6. And then on the inside, we've got the r squared and the r. So r to the third minus r to the third. So our q term ends up being 40.66666 times 10 to the 3 millimeters to the third. And then the t term. So the t term is the thickness of the section across which we're kind of measuring this transverse shear stress. So again, if we're taking the q for this entire area up here, then our thickness here is that plus that. So the thickness of the shell is 10 millimeters. So the twice that gives us a 20 millimeter a 20 meter section over which the shear stress is shared. So 600 newtons times 40.6 times 10 to the 3 millimeters to the third divided by 2.9 times 10 to the 6 millimeters to the fourth times 220 millimeters. Again, units cancel out to give us, got 3 of those on the top, so cancel out this one and 2 of those, gives us newtons per millimeter squared, aka megapascals. So once everything there is multiplied out and divided, we get 4.2 megapascals. And that again is on our little cube here, on our little cube face that's acting downwards. Actually, yeah, just right here. So we got the 4.2 megapascals that's going to be pulling this thing down, and we got the 15.5 megapascals that's going to be pushing it up. So overall, the shear stress on this on the positive, let me just double check the coordinate system. Yeah, okay. So the shear stress on the positive y face of pointed in the positive z direction is 11.3 megapascals. And again, because of that, we also need to have shear stress in the on the positive z face acting in the positive y direction in order to counterbalance that. So, and obviously on some of the hidden faces, if we kind of just we'll look at it from the from this side, it's doing this, doing this, doing this, and it is doing this. So that's how shear stress developed. If you have shear stress on one of these faces, then you have to have a counterbalancing force on this other face to make sure it's not that the net force is 0, and then you need to have these two in order to make sure that the net moment is 0. So you get the shear stress developing on all 4 faces. But when we report that, we just we only report one stress per one stress per side, basically. So our stress state at A is going to be just the 11.3 megapascals on the YZ and ZY. And then everything else is 0. There's no other axial stresses occurring, and there's no other shear stresses occurring in any other directions. So that's that.